Test, mic 1, 2, we're live. Twitch.tv/math happens. Making the announcement on Canvas. Do. Yo, what's good, Susufs, bro? I know what it says. I'll call you Sus. Right. I'll give it like another minute. Usually either people tune in right away or they don't tune in at all. So I'll give it just a quick sec. Oof. So what, you left the perimeter one blank and then typed both answers into the first one? Is that what you're saying? Alright, so I'm going to take it that the people who are going to show up live are here. I see that we have a few viewers. So we are looking at lesson 4.1, the start of unit 4, the start of looking at congruent figures. So what does the word congruent mean? I've used that word before, kind of assuming that people kind of know what that word means. But it means two figures are congruent if they have the same size and shape. So when you reflect something, when you rotate something, when you translate something, the image and the pre-image are congruent because they're the same size and shape. When we dilate something and make it bigger or smaller, the pre-image and the image are not congruent because, yeah, they might be the same shape, but they're not the same size. Two plane figures are congruent if and only if one can be obtained from the other by rigid motions. That's why we do transformations before this unit, because transformations helps us determine whether two figures are congruent. So, here are just some quick statements of congruence. You can think of congruence as like an equal sign. So, of course, an object is congruent to itself, right? I am equivalent to myself, right? So, yes, something can be equal to itself or congruent to itself. And this is saying you can flip the statement around, right? 2 is equal to 1 plus 1, and 1 plus 1 is equal to 2. You can flip a statement around. That's easy enough. And then this one is saying, well, if object 1 is the same as object 2, and object 2 is the same as object 3, well, then object 1 and 3 are also the same. Okay? So you can read back through those if my short explanation there didn't make sense, but I have a feeling that you'll probably be all right. So we're asking, are these figures congruent? So you look at these two guys. Are they congruent? I hope you instinctively say, yes, they're the same, right? They're the same size. They're the same shape. And how... I wish... Oh, I'll do this. So, what is the rigid transformation? Well, I can translate it, right? And prove, so to speak, that they are the same. This is essentially evidence that these two shapes are the same. If I translate right 1, 2, 3, 4, 5 and up 1, 2, 3, I can show that these two things are the same. So why are they congruent? P, S, Q, R. How do I want to phrase this super short? Translate. How about I just use function notation? Translate. What did I say? 1, 2, 3, 4, 5. Right 5 up 3. Quadrilateral J, K, L, M, and it's equal to quadrilateral P, Q, R, S. Okay? That's our evidence that they're the same, that they are congruent. Clearly, these are not, because they are not the same size. So that's what I'm going to say. They are different sizes. So something is congruent if you can essentially show that it's congruent by some type of transformation. When something's completely different size, then it's pretty easy that it's different and not congruent. Use function notation to describe a sequence of transformations that will map ABCD onto RST. So what we're saying is, yes, this is congruent. Yes, these are congruent. So prove it, right? What are the transformations that will take me from from RST to ABC, or the other way around? ABC, what does it say? It says specifically to go ABC to RST. So how can we go from this guy to this guy? Well, I think the first step that we should do is translate it down. You see what I'm getting at there? You realize what's going to happen there? Once I translate it down, how far down did we go, by the way? 1, 2, 3, 4, 5. So let's go down 5. And then what? What should we do with it? We should, hopefully you see it with me, we should reflect it, right? Flip it across the y-axis. And when we flip it, we're going to, I don't have a flip feature in this app. I really wish I did. That would be nice. Once we flip it, we're going to see, oh, it's going to match up perfectly. So the next step would be to reflect across the y-axis A prime, B prime, C prime, and it's going to give you triangle RST. Make sense? Hopefully, right? That's why they're congruent, because there's a sequence of transformations. So what's the transformation on this guy? Well, you could look at this a couple of ways. Let's see. It looks like we really need to turn it, right? It looks like we really need to turn it. So if we were to turn this 90 degrees counterclockwise, right? Because this would be 90, 180, 270, all the way around. If we were to rotate this 90 degrees, I'm gonna spoil it for you, so I don't have to look up the rules. I'm gonna spoil it for you because I have the answer right here in front of me because I did it ahead of time. When we rotate 90 degrees, when we rotate this figure 90 degrees, it's gonna end up right here. Ugh, I didn't want it to click like that. Gonna end up right there. That is a 90-degree turn. So when you rotate the triangle DGF, I think I'm going to choose a thinner font. If you rotate the triangle DGF 90 degrees, you end up right here. If you remember the rules, we've used them before. I mean, I don't have them memorized. Either do you. Right? But I'm letting you know that when I turn it 90 degrees, it's going to end up right here. Okay? And then I need to move it up 1. We need to translate up 1. Okay, so a little tedious to write that out. Lucky for you, you're not going to be writing that out very often. But the point is why are objects congruent? They are congruent because there is a set of transformations that takes me from object 1 to object 2. Okay, right here, for each pair of congruent figures, we can find a sequence of rigid motions. That's the important part, right? There's no weird stretching. There's no weird dilations, stretching or shrinking. There's none of that, right? It's the 3 basic movements: reflections, translations, and rotations. Okay. So, when 2 triangles are congruent, the corresponding parts are the sides and angles that are images of each other. Okay? So notice here, right? what would be the corresponding parts in this picture? This figure translated downwards and became this, right? This side corresponds with this side, right? And this side corresponds with this one, right? They're the same, right? After the movement, right? When you look at these two figures, we know that this side is the same as that one, and this side is the same as that one, and this side's the same as that one, right? We know that to be true. And when we flip this guy, right, we know this side is the same as this one, and we know this side is the same as this one, and we know this side is the same as this one. Those are corresponding. They match up. So we call them corresponding. Okay. So when a statement is written like this, there's something very particular, okay? There's something super duper particular here. What we're saying is that R corresponds with M. And what we're saying is G corresponds with Q. And what we're saying is K corresponds with B. All right? That statement is written like that, so that way you know that, right? It's not just, what we're saying, here's triangle RGK. And here's triangle MQB. Did I draw it right? No, I didn't. Okay? How do I know I didn't draw it right? Because R has to correspond with M. And as this drawing shows, R is corresponding with B. This statement is written to make life super easy for you. It's not meant to make it harder. It's meant to make it easier. This statement is written in such a way to tell you that R corresponds with M. You get to know that. And G corresponds with Q, so on and so forth. So let me draw them prettier and properly. Here is triangle RGK, and here is triangle MQB. Okay? So what do we know? We know that this side corresponds with this side. And I've used tick marks once or twice before. Tick marks mean that, hey, this piece is equal to this piece, or the proper word now that we're using, congruent. Okay? So we know that this piece is congruent to this piece, and we know this side is congruent to this side, and we know this side is congruent to this side. Okay? Let's write those statements down, right? That's what these blanks are for right here. RG is congruent to MB. And RK is congruent to MQ. And GK is congruent to BQ. Okay? Just looking at this picture. Here's RG, here's MB. Here's RK, here's MQ. You don't even need to draw a picture to know this. Why is that? Because this tells you everything you need to know. RG is congruent to... Oh no, I drew this wrong. Oh no. Wow, I drew it wrong. I'm such a dummy. I'm sorry. Oh no, I'm sorry. This is Q and that is B, right? Oh wow, I'm such a dummy. R corresponds with M. G corresponds with Q. And K corresponds with B. So RG is congruent to MQ. This side and this side. And RK is congruent to MB. And GK is congruent to QB. And like I said, as I was starting to say there, and then I caught my error, we don't even need this drawing, right? I don't even need this drawing, deleting, right? I don't even need that because this tells me everything. So what angles are congruent? Angle R is congruent to angle M. Angle G is congruent to angle Q. And angle K is congruent to angle B. I don't even need the drawing to know that. Right? That's just a fact of this statement, right? That's just how it is. So this asks, what is another way to write this statement, right? I can draw a triangle real quick, right? And I can name this triangle BCA. I could name it CAB. I could name it ABC. There's lots of names, right? There's lots of names here that I could call this. So what's another way that I could name it? Well, how about I just start with G instead? GKR is congruent to. All right, well, if I'm starting with G, then I have to start with Q. QBM. Or I could write triangle KGR. See what I did there? I went backwards. Well, then that would be congruent to triangle BQM. This statement is meaningful. It has more meaning than just, hey, they're equal. It also tells you G corresponds with Q and K corresponds with B. It tells you so much more than just, well, they're equal. You want to find the distance across a river. In order to find the distance AB, you locate points as described below. Explain how to use this information and the figure to find AB. So identify a landmark such as a tree at A. All right, here's my tree. At A, place a marker B directly across the river from A. So this is apparently a river. Okay. And here's my marker at B. At B, turn 90 degrees, which we did. There's my right angle. Away from A and walk 1,000 feet in a straight line. Place a marker C. Continue walking another 1,000 feet. Place a marker D. Turn 90 degrees away from the river and walk until C aligns with A. So we walk, and then we turn and look, and we're like, oh, this C and A are lined up. So place a marker there at E. Measure DE. Well, the drawing has revealed the length of DE for you. It's 875. So, what are we doing here? What's the point of this? We're creating congruent triangles. We are creating congruent triangles, right? These two triangles are the same, right? This is 1,000. This is 1,000, right? So, well, I guess we haven't exactly shown that they're congruent. I'm leaping a little bit far there. They are congruent, but what we really want to stress in this moment is that there are corresponding pieces. So this side corresponds with this one because we're trying to make a match. If this one's 1,000, this one's 1,000. Okay. So what side of EDC corresponds with AB? Well, the 875 corresponds with AB. So that's side DE. What is the length of AB? Well, if they correspond, well, then that means AB is 875 feet. Corresponding pieces, I guess I should go back up to this statement, right? This was a pretty big statement that I didn't exactly read through and through. Corresponding parts of congruent triangles are congruent. That's a mouthful. Corresponding parts of congruent triangles are congruent. Right? It goes back to what I was saying here, right? The pieces that correspond with one another are congruent. It goes back to what I was saying up here, right? The pieces that correspond with one another are congruent. So now that I've made two triangles that are identical, aka congruent, we know that the corresponding pieces are congruent. The sides that match up are the same. All right, now we got a quick little algebra problem here. If EC is 7x minus 1 and AC is 20, what is the value of x? Well, we know, or why do we know that these two things are equal? Why do we know that? Because EC and AC are corresponding. Corresponding pieces of congruent triangles are congruent. If something's congruent, that's basically another way of saying equal. So those corresponding pieces are equal. And solve. Add the 1, you get 21. Divide the 7, you get 3. So, let's look at these 4 drawings or 4 examples to basically end it all here. When do we know that two triangles are congruent? Right? Like, how much information has to be true? What am I getting at here? Like, if I give you a triangle and I say this side is 20 long and this is 90 degrees, well, I can give you another triangle that also has a base of 20 and a 90-degree angle, but clearly they're not the same, right? Just because a couple pieces are the same doesn't mean the whole thing is the same. Let me give you another example, right? I can have a triangle that looks sort of like this, where the base is 30, and let's say this angle is like, I don't know, 25 degrees. Well, I can draw another triangle with the exact same measurements, right? This is 25 and this is 30, but clearly they're not the same. So what is enough? What is enough to declare, you know what? These two triangles are the same. What is enough? These are what's enough. If all 3 sides of a triangle are the same, we know if that the two triangles are congruent, right? If this triangle and this triangle have all the same sides, there's no ifs, ands, or buts about it. Those two triangles are congruent, and we call that side, side, side. There are methods for proving triangles congruent. And this is one of them. If you can show that all the sides are the same, then you know that the two triangles are congruent. We call that side, side, side. All right? So AB is congruent to XY, and YZ is congruent to BC, and AC is congruent to XZ. And ta-da, these guys are congruent. We know that they're congruent because all 3 sides are the same. It's impossible, what I was getting at up here, right? Where I was drawing triangles that had some similar characteristics, but not all the same, right? It's impossible to draw a triangle that has all 3 sides the same length and they not be the same, right? It's simply going to be a rotation, a translation, or a reflection, right? Okay, what's another thing to know, like for a fact that they're congruent? If 2 sides and an angle are the same, we call that side, angle, side. If the angle is between the sides, okay? You notice that? Look at the phrasing. Side, angle, side. SAS. the angle has to be between the sides. Or we get kind of similar, angle, side, angle. The side is between the angles. You see that? How the side is in between the two angles. Here's angle 1, here's angle 2. And the side is in between those two angles. Okay? So we say that's angle, side, angle. And then the last method of congruence is angle, angle, side. If two angles and a side, angle C with Z and angle A with X, and AB with XY. So whether the side is between the angles, or after the angles, it really doesn't matter. If two angles are congruent, therefore the triangles are congruent, basically. Two angles and a side. So these questions are asking, are the triangles below congruent? If so, then by what method are they congruent, right? You look at this picture, right? They're in slightly different orientations, right? But based on the information given to you, are they the same? And what method proves them? So we have an angle followed by a side. Sounds familiar, right? Angle, angle, side. So these guys are congruent by angle, angle, side. What about this? Angle, side, angle. Angle, side, angle. Yeah. Those are also congruent by angle, side, angle. All three sides are the same? Okay, that's congruent by side, side, side. And this is side, angle, side, angle, side. That's congruent by side, angle, side. So all four of these were congruent. You might be asking, well, okay, it was obvious they were congruent, right? Because they looked the same, right? Well, let's just say I gave you this triangle and this triangle, and they look the same, but not drawn to scale, okay? Not drawn to scale. Are these two triangles congruent? Spoiler alert, they're not going to be. But are these two triangles congruent? I know two sides and an angle. Sound familiar? Side, angle, side, right? Two sides and an angle. But is that angle between the sides? No, it's after the sides, right? So it's possible to have, and I could draw it for you right now. Here's a side. I could draw you, this might take me a quick sec to draw. Here's a side. And here's another side. And here's that angle. And let's say this is 30 degrees. Well, what if I took that same angle and instead opened up? Oh, it's tough to do these. I'm trying to show you an example where that wouldn't match up. I'm getting distracted from the point. The point is, I'll try to have some examples for class. The point is that these two triangles, there's not enough info, right? It all comes down to why are these triangles congruent or why are they not? These triangles are congruent because they follow one of these four things. These guys are the almighty grail, right? There's not enough info in this drawing, right? This is angle, side, side. And my funny joke for you, ass is not a thing, okay? Ass is not a thing. ASS is not a proper way of proving triangles congruent. Trying to find a good picture for you. Let me know if this picture right here makes sense. Take a look at this picture here. This is saying why does side side angle and angle not work? Well, take a look at this. This is a 30-degree angle, right? This side is 11 and this side is 6. You could have this angle right here come inwards like so, right? And this is a triangle that has a side of 6, a side of 11, and an angle of 30 degrees. Well, erase that from your mind and look at this one now. This also has a side of 6, a side of 11, and an angle of 30 degrees. They're not the same triangle. They have the same characteristics, angle, side, side, but one is different from the other. Angle, side, side is not enough to prove congruence. And angle is more obvious, right? Who cares if the three angles are the same, right? You can have a big triangle and a small triangle. Just because their angles are the same doesn't make them the same size shape. All right. We did it. Not too shabby. Thanks for watching. I'm gonna get this posted once I finish Algebra 2. Which, speaking of, I should make an announcement for Algebra 2. Do. Posting. Posted. You got anybody here for Algebra 2? Anybody out there yet? I'm gonna go ahead and get started. Just make sure get this replay out. All right, so I'm gonna be primarily Alright, so Algebra 2 stream starts now. I'm gonna be mainly talking to myself here because there's not too many people in the chat right now. There's nobody really that I can see. No one's spoken up, so here we go. Solving polynomial equations. We're still doing that. We're still solving polynomial equations. But something to note, something of interest, is there are 4 terms now, right? We're looking at something like so. There are 4 terms. And what this example is trying to show you here is that the first 2 terms should have something in common. And the second 2 terms will have something in common. Okay? Let's look for that. What do the first 2 terms have in common? What is their GCF? The GCF is x squared. When you take out x squared, you're left with x plus 6. Okay, and look at the next 2 terms. What do they have in common? A 4. So let's say I pull out a 4, I'm left with negative x minus 6. Now the goal here is that when you factor out that thing that's in common, you should be left with the exact same expression. We were not left with the same expression. It's off by a little bit. Well, what should we do then? Take a look at what I pulled out here. I pulled out a 4. What if I pulled out a negative 4? Then I'm left with x plus 6. Hello. Then I'm left with x plus 6. I'm doing Algebra 2 right now. Unless you're here for Algebra 2, but I was thinking you were the Emily from my Geo class. So, now I'm left with the same thing. So, how do we conclude this? You take the 2 terms that we factored out, and the thing that matched. And we're done. We factored it. I'm not done, but we factored it. So once we're done factoring, what do? We set our factors equal to 0 and solve. Add the 4. Take the square root. X equals plus or minus 2. X equals negative 6. We got 3 solutions. Boom. It's that simple. I really like grouping. Let me do it a little bit quicker just to show you like how not stressful it is, right? I took the time to explain it there. You could always rewind a minute and 20 seconds to see me go through and through that one more time, but I'm going to say it real quick. Look at the first two terms. What's the GCF? X squared. And I'm left with x minus 5. Look at the second two terms. What's the GCF? Remember, when we yank out the GCF, we need them to match up. So I'm going to pull out a -9 to make sure this says x minus 5. See, I didn't just pull out 9, I pulled out -9. And now they match. And now that they match, you take the two terms from the outside, that's factor number 1, and you take the thing that matches, that's factor number 2. Set those factors equal to 0, and you have your solutions. Voila. Let's do it again. Maybe even a little more quicker. Look at the first two terms. What's the GCF? X squared. I'm left with 3x minus 1. Look at the second two terms. What's the GCF? I don't see a GCF. Okay, well, everything has a GCF of 1. That's okay. Maybe they don't have a number in common. Maybe it's just 1. All right. Well, there's factor number 1, the two numbers on the outside. And there's factor number 2, the things that match. What do we do with our factors? We set them equal to 0. And we solve. Subtract the 1, we end up with -1. So when you take the square root of -1, we end up with plus or minus I, because that's imaginary. Add the 1 over, divide the 3, we end up with 1/3. Do it again, one more time. Look at the first two terms. You ask yourself, what's the GCF? You might look at that and say 2. You might look at that and say 4. You might look at that and say 8. You need the biggest one, so don't make that mistake of not choosing the biggest one. 48 is divisible by 16. 16x squared is the GCF. And I'm left with x minus 3. 3 times 16 is 48. Remember, it needs to match. I look at this and I'm like, well, they don't have a GCF. I'm going to pull out a -1. Right? If I just pulled out a +1, I'd be left with -x plus 3. Right? It wouldn't change the sign at all. But by yanking out a -1, we're flipping the signs there. And now it matches. Great. So whatever your two terms are on the outside, that's factor number 1. And whatever the two terms are that match, that's factor number 2. What do we do with our factors? We set them equal to 0. We did it. I think those are super easy. I really do. I like the rhythm. I like the pattern. That is the point. Yes, indeed, Slow Towner. If they don't match, well, if they don't match, one of two things is true. Either this method of factoring doesn't work, or 2, you've done it wrong. For the sake of the assignment, right? All of these problems are rigged so that it does work. So on the classwork, if for some reason it doesn't match up, you've done it wrong. So yes, with grouping, the idea is the point is that these will always match. All right. So there's grouping, and when and why are we using it? The answer to both of those questions are the same. When do we use it? When we have 4 terms. Why are we choosing to use this? Because we have 4 terms, right? That's new, that's different, that's unique, right? When there's 3 terms, that's a highlighter. When there's 3 terms, what is there to group, right? What is there to group? There's going to be overlap, right? Because there's 4 terms, it's kind of completely out of left field or right field or whichever way you want to say it. We need a new method. This is a moment where my U method would not work, right? Because this is different. There's 4 terms. So we got to use grouping. All right. So what about when there's 2 terms? We've got a cubed term and a constant. A cubed term and a constant. A cubed term and a constant. Well, we call this either a sum of cubes or a difference of cubes. And it will always follow this pattern for a sum, and it'll always follow this pattern for a difference. Take a look at these examples. It says a cubed plus b cubed. So this is x cubed plus, it's the number 8, but what is 8? 8 is 2 cubed. So a is x and b is 2. As I plug it into this equation, we have x plus 2, a plus b. And then a squared is x squared. And then a times b is 2 times x. And b squared is 2 squared. You see how that's matching up? Take a look at this one. This is 2x cubed. And this is 1 cubed. So a is 2x. B is 1. See how that's matching up there? What's good, Uzi? It's nice to know your cubes, right? It's so that way they stand out to you, right? You're not like, is that a perfect cube? What is that? Is that 5 cubes, 6 cubes? It's nice to have them handy, okay? So 1 cubed is 1, 2 cubed is 8, 3 cubed is 27, 4 cubed is 64, 5 cubed is 125. No, it's not. Yeah, it is. 525. 6 cubed is 216. 7 cubed is 343. That's 1,000. I don't know the rest. I knew quite a few there, right? Give me some credit. I'm gonna double check 6 cubed. Yep. Okay. So 8 to the third. Just plugging this into a calculator on my end. 512. 9 to the third. 729. I think 11 cubed is 1,221. 331. Oof, that was close. And then 12 cubed is, all right, 1,728. So it's just nice to have those handy. So let's look at B because it's got a little more going on. What's the first thing that you should always do? And I kind of didn't mention it in these problems, which is my mistake, because technically you should always be looking for a GCF. Always look for a GCF. So this is divisible by 4. So let's divide everything by 4. 108 is divisible by 4. 108 divided by 4 is 27. So when I divide everything by 4, I end up with x cubed minus 27 equals 0. And now all of a sudden, I'm looking at something a bit more manageable, right? This is x cubed minus 3 cubed. Why am I writing it like that? Because you really need to know that a is x and b is 3. This is a difference of cubes because of the subtraction sign. And I'm going to plug it in to this equation. A minus b, so x minus 3, times a squared, so x squared, plus a times b, which is 3 times x, or 3x, plus b squared. 3 squared is 9. See what I just did there? Right? You see how I just plugged all that in? So, let me tell you something here. When we follow this pattern, the second half isn't factorable. Okay? What am I getting at? What do I mean by that? We can look at this and go, the solution is 3. This, spoiler alert, I'm just telling you right now, anytime you have a difference of cubes or a sum of cubes, I'm telling you right now that this thing right here is not factorable. It's not. It is not factorable. So, my suggestion would be to use the quadratic formula because of that, right? When we set our factors, let me move this up. Let me move this up a notch. Ooh. Oh, I accidentally caught that 0. Let me move this up a little bit to give myself room. When I set this equal to 0, this looks like a normal everyday problem, and it is. It is. But I'm being a nice teacher, and I'm telling you something that's going to happen every single time. You can't factor it. You can't. It's not going to happen. All right? So use the quadratic formula. Let's remind ourselves what the quadratic formula is. Negative b plus or minus the square root of b squared minus 4ac all over 2a equals 0. Or not equals 0, but equals our solutions. So let's plug that in. Negative 3 plus or minus the square root of 3 squared minus 4 times a times c all over 2a. Let me know if I've lost you on what I'm doing here, right? But I hope I'm doing all right. Let me give a 10-second recap, right? I followed the pattern and got to this point. Well, what do I do from here? Set your factors equal to 0. This gives me an easy solution. This one, not so much. I have to use the quadratic formula, and that's where I'm at. So negative 3 plus or minus the square root of, to save my hand and to save you time, I'm just going to plug that into a calculator. 9 minus 4 times 1 times 9 is 36. So 9 minus 36 is negative 27 all over 2, which is equal to negative 3 plus or minus. Let's address this situation. Let's address that situation. What is that about? Well, let's pretend it was positive for a moment. How do we handle this? I think we've done this once or twice, and you definitely did it in Algebra 1, and you might have done it a little bit in geometry too. How do we simplify a square root? You look for the biggest perfect square. This is 9 times 3. I can take the square root of 9. That's 3. But I can't take the square root of 3, so I'm left with 3 root 3. Remember simplifying radicals like that? Some of you might have a calculator that's nice enough to do that for you. Like an actual calculator. So, in the end, negative square root of negative root 27 is 3i root 3. I don't mean to lose you or to overcomplicate it, but I mean, you're nearly at the end. Let me just tell you right there, you're nearly at the end. But I want to simplify that, okay? I want to simplify that square root, and I'm left with 3i root 3, and then don't forget it's all over 2. And there's our 1, 2, 3 solutions. 1, 2, 3. All right, let's do it again. I can show you my work if you need me to go back over there. Just let me know. But let's just jump right into it and do it again. This is x cubed plus 2. Well, this example's already up here. Lame. Let's change the number. Let's change the number, eh? Well, I guess we didn't. Well, if we need to do one more, I'll do that one. Let's look at this one. This is x cubed minus, what was 1,331? That was 11 cubed. So once again, we have a difference of squares because it's subtraction, where a is x and b is 1,331. No, it's not. I misspoke. 11. And honestly, what I just did is a very common mistake. A lot of students will look at this and go, well, a is x and b is this number. No, how did you get to this number? It is 11 cubed, and b is 11. Okay, your 11 is your b value, not the big number, but the small number that got you there. We cubed 11 to get 1,331. 1,331 is not b. 11 is b. And 11 cubed gives me 1,331. All right, and then we use the equation, which, let me write it down so that way I'm not zooming back and forth. A minus b times a squared plus ab plus b squared. All right, so there's the equation from the tippy top there. So a minus b, a squared times a times b, that's 11x, and then b squared, that's 121. So like I said, this one gives you your easy solution. And spoiler alert, once again, this is not going to factor. This is not. It's not going to factor. So we use the quadratic formula, which is negative b plus or minus the square root of b squared minus 4ac all over 2a. What does that get me? 11 squared is 121 minus 4 times 1 times 121. What is that? 4 times. So I end up with negative 363 all over 2. (363) is divisible by... What is it divisible by? 363, is it divisible by 4? No. What's the bet? So this is what I'm doing. I guess I'll show you my screen. But I'm looking at 363 because, again, now I'm at that point. Let me go back. Now I'm at the point where I'm like, I need to simplify that square root somehow, right? I need to simplify it. So my biggest perfect square was 9 in this situation. That's because I saw it immediately, right? I think we all know that 9 times 3 is 27. What's my biggest perfect square here? I'm just trying out some numbers. So 363, is it divisible by 4? No. 363, is it divisible by 9? No. 363, is it divisible by 16? No. 363, is it divisible by, what's the next one? Not divisible by 36. Not divisible by 25. 49, maybe? Is it not divisible by anything? 64? I don't, maybe it's not divisible by anything. 363, is it divisible by 121? Oh, that makes sense, right? Because it came from 11. Oh, that kind of makes sense. So 11 squared is 121, right? And 363 is divisible by 121. So going back here, if I'm simplifying this radical, the square root of negative 363, that splits up into 121 times 3. The square root of 121 is 11. It's negative, so it's imaginary. And the 3 is left over. Whoa. 666 in your search bar. Yeah, it's because I was trying to figure out 6 cubed earlier. when I wrote that at the top. You actually made me think for a second, like, how did that get there? Yeah, it's because I did 6 cubed earlier. All right, so I end up with negative 11 plus or minus 11I root 3 all over 2. All right, one more. One more. This one is a sum of cubes. And this one's got some more numbers going on. We got 64, 125. Let's be careful with this. What is 64? 64 is 4 cubed. So this is 4x cubed plus 5 cubed. A is 4x, B is 5. It is so important that you, if you do anything, right, if there's a step that you shouldn't skip, it's that you should write this down. Write that down and make it crystal clear what is A and what is B. So that way when you go to plug it in to the equation, which again I'm going to write down so that way I don't have to keep scrolling back up and forth and whatnot. You can tell that it's practically the same. It's just that, oh, we have a plus now and we have a minus now. It's nearly the same. So let's carefully plug this in. 4x plus 5 times a squared is 16, 4 squared, and so 16x squared, minus 4x times 5 is 20x. 4 times 5 is 20, so 20x, plus b squared, 5 squared is 25. This gives you the easy solution of negative 5/4. And as I said earlier, and I'm going to say it one more time, this doesn't factor. And I mean, this is especially gross with this lead coefficient of 16, right? I mean, it's not looking too pretty at the moment, okay? So we're going to plug it in carefully. What color should we use? Let's spice it up with a pastel color. Pastel green here. Negative b. So negative. Should I write them out over here? A is 16. B is negative 20. C is 25. So negative b plus or minus the square root of b squared minus 4ac all over 2a. So a negative 20 results in a positive 20, plus or minus the square root of that is 400 minus 4 times 16 times 25 is 1600 all over 32. I end up with 20 plus or minus the square root of, what is that, negative 1200 all over 32. And again, when we simplify this radical, we're looking, I'm going to do it off to the side here. I'm looking for the biggest perfect square. I actually know this one offhand. It's 400. 400 times 3, right? Think of 12. What's the biggest perfect square in 12? 4. 4 times 3. Up the ante, right? It's 1200 now. So it's 400 times 3 gives me 12. So 400 is 20 squared. So the square root of 400 is 20. I can't take the square root of 3. So 20i root 3. There's something a little extra, though, that we can do on this. All these terms, 20, 20, and 32, are divisible by 4. So we can actually reduce the fraction down to 5 plus or minus 5i root all over 8. Because I can reduce the fraction. If you noticed, it's not a coincidence here. At least I don't think it is. I don't know. Should we take my word for it? I don't think it's a coincidence that 11 and 11 matched. That 20 and 20 matched. That 3 and 3 matched. I don't think that's a coincidence. I think that happens every time. I think. I'm pretty sure. I bet there's a proof for that somewhere. Before I just wrap it up, I do need to go at about 3 o'clock. Do we have any questions for me? Those of us still hanging out in the chat? Anything I should go back over? What I did with my water bottle? Clear over there. Anybody got a question? Well, all right then. With that being said, I think it's a pretty easy lesson. So we'll go ahead and call it there. I'll get this replay uploaded. Have a lovely evening. Thank you for watching. I'll see you next time.